Let's talk about an invisible force that powers, well, pretty much your entire life. It's a force that's so precisely controlled it can run a microchip, but at the same time, it's so powerful it can be incredibly dangerous. Today, we're going to pull back the curtain and look at the fundamental rules that tame electricity.
So take a close look at this little thing. I mean, there are literally thousands of these inside the device you're watching this on right now, and its entire job is to fight. It's specifically designed to push back against one of the most fundamental forces in the universe. What you're looking at is a resistor. These are the unsung gatekeepers of our electronic world, and they come in this incredible variety of shapes and sizes. You've got ones that are barely bigger than a grain of rice, all the way up to this beast that you could hold in the palm of your hand. But no matter what they look like, they all share the exact same job. And that job is, you guessed it, simply to resist. A resistor's whole purpose in life is to provide a very specific, carefully measured amount of opposition. You can think of it like electrical friction, something that slows down the flow of electric current. It's basically a traffic controller for electrons.
So how do we actually predict and control this opposition? Well, it turns out every single resistor, no matter how big or small, has to follow a very strict rule book. And the first and most important rule in that book is called Ohm's law. Now, to get Ohm's law, you just need to wrap your head around three key ideas. The first one is voltage. The easiest way to think about it is as electrical pressure, right? Just like water in a pipe, electricity always wants to flow from a place of higher pressure to a place of lower pressure. And that pressure difference is what we measure in volts. Okay, so if voltage is the pressure, then next up is current. This is the actual flow of the electricity, and we measure it in amperes, or amps for short. So going back to our water pipe, this would be like the amount of water actually moving through it at any given moment. And that brings us to the last piece of the puzzle, resistance, which we measure in ohms. This is that opposition we were just talking about. In our water pipe analogy, resistance is like a narrow spot, or maybe a kink in the hose, that restricts how much water can get through, no matter how hard you're pushing it.
Back in 1827, a German physicist named George Simon Ohm was the very first person to figure out the mathematical relationship between these three things. Now, his original wording was, let's just say a little dense, talking about electrical forces and reduced length, but he was on to something huge.
Thankfully, today, we've boiled all that down to this beautiful, simple formula. V equals I times R. Voltage equals current multiplied by resistance. This is the absolute cornerstone of electronics. It means that all three of these things are locked together. If you keep the resistance the same, but you crank up the voltage, the current has to go up. It's a simple, powerful rule. And here's what that looks like in the real world. In a super simple circuit, you've got a battery providing the voltage, that's the pressure. Then the resistor adds the resistance, the squeeze in the pipe. And Ohm's law is what lets us calculate exactly how much current is going to flow through that circuit as a result.
But what's really interesting here is what happens to all that energy when you resist it? I mean, you're literally fighting against a fundamental force of nature. That energy has to go somewhere. It doesn't just, vanish.
And this brings us right back to our first question. If a resistor's only job is to provide a specific number of ohms, why the huge difference in size? Why don't we just have one size that's good enough for everything? I mean, just look at these two again. It's totally possible that both of these have the exact same resistance value, but one is this tiny little speck and the other is a massive finned block of metal and ceramic. And the reason for that difference is all about the unavoidable consequence of resistance. The answer is heat. Simple as that. When a resistor fights against that flow of current, it converts the electrical energy into thermal energy. In other words, it gets hot. So a resistor's physical size isn't really about its ohms, it's all about its ability to get rid of that heat without melting or catching fire. More surface area just means it can cool down faster and more effectively. And this energy conversion is described by another fundamental rule, Joule's law. It tells us that the power that gets turned into heat, which we measure in watts, is simply the current multiplied by the voltage. Ever wondered why your phone charger gets a little warm when you plug it in? That's Joule's law in action. Or think about a toaster. Its whole job is to get crazy hot by using wires with just the right resistance to generate a ton of power as heat. That giant resistor we saw isn't for high resistance. It's built to handle high power. Okay, so now we get the rules that govern all these little components in a circuit. But here's the thing. These laws of voltage, current, and resistance apply everywhere. And that includes to us. And this is where understanding them really becomes a matter of life and death.
So, let me ask you this. How much current do you think it takes to actually be dangerous to a person? The answer is shockingly small.
100 milliamps. That is just 1/10 of a single amp.
Yeah, that tiny little amount of current is considered the threshold where an electric shock can send the heart into what's called fibrillation. It's this chaotic, useless quivering that can absolutely be fatal. Now, to put that in perspective, a standard circuit in your house is probably rated for 15 or 20 amps. That's 150 to 200 times that lethal amount. You know, our whole modern understanding of electrical safety is pretty new. If you go back to the 19th century, the dangers were so poorly understood that electricity was basically a party trick. There are historical records from the London Electrical Society in 1837 showing that visitors were entertained by getting powerful shocks from new gadgets. This illustration from 1892 shows exactly that. It's a person being intentionally shocked by a machine called Clark's induction coil. And this was just seen as acceptable lab practice back then. It's a really stark contrast to the strict safety rules we follow today, rules that are built on the very laws we've just been talking about. So let's zoom out. What's the big picture here? What do all these invisible rules really tell us?
Well, it all connects, right? We use resistors to control current, and we understand that relationship because of Ohm's law. But Joule's law reminds us that this control creates heat and uses a power. And when we lose that control, even a tiny amount of current can be deadly. These rules aren't just for engineers. They are the reason we can all safely use this incredible power every single day.
From the phone in your hand to the lights in your ceiling, these invisible rules of pressure, flow, and opposition are constantly at work, silently powering our entire world. Now that you know the rules, how are you going to see things differently?